going to continue our discussion of MRI. But before we do, any questions from last time or about course logistics? So we're in week 9. We have one more week of lectures. And then project 2, I think everyone hopefully has had a chance to look at their feedback, and just the next day or so is you can sort of revise and resubmit as needed. Okay. So any questions about that? No. Okay. All right, so today what we're going to do is we're going to review a little bit of what we talked about in terms of least squares and minimum norm solutions, talk about parallel imaging, which is now very standard, compressed sensing, which is becoming more adopted, and then deep learning, which has just come online in the last few years. And then hopefully we'll be able to start some discussion of relaxation. So we'll switch gears a little bit and go back to sort of T1 and T2 and what they mean. And then just in terms of some notes on the quiz, the pre-lecture quiz. So, the main thing to keep in mind is anytime we're talking about sampling in K-space, then it's related to the FOV. And anytime you're really talking about how wide you go in K-space, then that's typically related to the resolution. Okay. And the other design problem that comes up quite a bit in MRI is if you have, say, your GX gradient and your GY gradient, right? And in the homework and the pre-lecture quiz, right, there's these dephasers, which their job is to take you out to some initial place in K-space, right? And so let's say this is KX and KY, and I want to go farther out in KX. I want to go out to here, right, in KX than I want to do in KY, right? So which area is going to have to be greater, GX area or GY area? GX, right? Because I need a bigger gradient. So let's say I had a certain, amplitude that I could play out, a maximum amplitude I could play out. Let's say minus A here. Okay. So I could actually get the area in this amount of time, right? Maybe with the GY gradient, but it would take me this amount of time to get the sufficient area in the GY gradient, right? So one of the one that has to go farther out in K space is going to be sort of my limiting factor. And so generally in MR, we want to push the equipment, but we never want to push it that hard, right? It's sort of like, if you're traveling with your friend and they're walking slowly, you don't necessarily need to run to get to the restaurant first, unless you feel like you want to get there first and just wait for them. Okay. So anytime you really the gradients, they're, as we talked about, they're really these high-powered machines, and so in general we don't tend to push them unless we need to. So in this case, instead of playing my gradient, although I could play my GY gradient very quickly, generally the design trade-off would be I would actually take my time and use this area here. Okay. So if I know it's going to take me a certain amount of time to play my GX gradient, I might as well just wait and lower the amplitude and play my GY gradient. Right. So that's just sort of how that pre-lecture quiz question is also related to what people do in practice, right? We typically look at both gradients and then we just adjust the timing such that we just sort of let the limiting factor decide. Right. So are there any other questions about pre-lecture quiz? Okay. All right. So this was the timeline we went through. And as we talked about last time, the thing about MRI that's pretty different from CT is every name you're seeing there, aside from Romer here. So he was at GE. Everyone else was either a grad student or a postdoc or a professor. So most of the innovations in MRI actually have come from academia and then gone to industry, as opposed to the other way around. Okay. Typically industry is really good at taking what academia does and making it work robustly. But the fact is that early on I believe in the early 80s, probably the manufacturers, because a lot of people were in academia, they made a conscious decision to make the software open. So when we buy a scanner, we sign a research agreement with either GE or Siemens or Canon or Philips. And so we have access to their source code, and then we can modify their source code. Okay. So the manufacturers have benefited from that a lot because then they have all these people inventing things for them. All right. Where CT has been a lot more of a closed environment. It's very hard to get the source code for CT. And so that's why most of the innovation still is happening in the companies. Right. Okay. So last time we talked about this picture that we've had from the very beginning of we want a certain object, and in MR, we're acquiring the data in Fourier space, okay? And when we think about it, it's most easily intuitively to think about a 2D object because we think we see things in 2D, and then we have a 2D Fourier transform, right? And luckily, with MATLAB or Python, you don't have to think about it. You just say, do a 2D FFT for me, and you don't have to think about how it does it, right? But if you want to actually break it down and say, well, what if I want to do this, using more basic commands in MATLAB and sort of linear algebra commands, then what you need to do is you need to take this object here and you need to make it into a column. Okay, so in MATLAB, this m just equals, you just use the colon operator in MATLAB, okay, and just takes a column by column, all right? And so this 2D matrix becomes a 1D column vector. This 2D matrix becomes a 1D column vector, okay? And then the relationship between these is every row here in my encoding matrix is just one of my 2D Fourier sort of a complex phasor, okay? So it for every row, it's going to have a certain kx and a ky in it. So this is going to represent a spatial phasor pattern, a 2D spatial pattern, but it's just in a vector form now. All right, so you're just taking your image here and multiplying it by that 2D spatial pattern, but everything has been vectorized. All right. And the interesting thing about this is every row here is orthogonal to every other row because it's a Fourier transform. Okay, so one of the properties of Fourier transforms is if you think of these as vectors, every vector is perpendicular to every other vector in this encoding matrix. All right, so that's the geometric intuition you want to have is the Fourier transforms. Why they're so useful and why they have such nice properties is because the vectors are orthogonal. All right. And in the fully Fourier encoded case, where we satisfy the Nyquist requirements on FOV and resolution, then this matrix E is going to be a square matrix. Okay. And so in that case, went to a square matrix, and because all the columns are orthogonal, we know they're also independent, right? If things are orthogonal, then they're going to be independent. So therefore, we know there's going to be inverse, and the inverse actually has a very nice form. It's just the complex, the Hermitian transpose or the complex conjugate of the matrix. So this is essentially just saying what we did with integral, but saying you either have, you can multiply by E to get the Fourier transform, and the inverse transform is just E to the H, okay? Which is just a complex conjugate. And we saw that in the Fourier transform, where the Fourier transform had things like E to the minus J 2 pi kx, right? And then the inverse transform had things E to the plus J 2 pi kxx, okay? So that's what we're seeing. So everything is really nice and simple in Fourier domain. We talked a little bit about overdetermined equations, and this is the case where you're still doing full Fourier, but you just have a lot of coils. And so in that case, we ended up with the least squares estimate here. And this was, remember, when you have an overdetermined case, then there may not be a unique solution, but there is a solution that minimizes your error. Okay. And what we want to talk today about is review what happens in the underdetermined case. All right. So now you see this output vector here is a smaller length than the input vector. Okay, so that means if I had like a 256 by 256 image, maybe I only acquire half the k-space line, so I don't have as much data. This matrix gets smaller, and now, as you know from linear algebra, I have less equations and unknowns. And so it's an undetermined system, so there's multiple solutions. There's not a unique solution, right? And the solution that we like to do, that we do, if we do the inverse transform, turns out to be the minimum norm estimate, which is just here, okay? And so this will minimize the size of this estimate, right? So that's why it's called minimum norm. We talked a little bit about how quickly using multiple coils sort of happened. So over a course of about 20 years, it went from buying a system with one coil would be standard, and now buying a system with 32, 128, 64, those are all fairly standard options now, right? Okay, this was the overdetermined case where we basically have an overdetermined set, and we're going to review this just because it sort of gets us, we want to review this idea of coil sensitivity. So the idea is once you have multiple coils, okay, the key insight is each coil only sees part of the object now, right? So if I have a coil here, it's going to be fairly sensitive to the spins close to it, but not so sensitive to the spins out here, right? So there's going to be a coil drop off in sensitivity. If I put a coil here, it's going to be sensitive to the spins close to it, and then there's going to be a drop off. Typically, the rule of thumb is whatever the radius of the coil is, it's sensitive to things, a depth of that sort of diameter radius on that order, right? It's not to say that it doesn't see other spins, but it's mostly sensitive to that region, proportional to its diameter. All right. So this is an example here where there's just two coils, and you can sort of see the coil on half of the brain is much more sensitive to this side of the brain than this side of the brain, and the coil on the other side of the brain is more sensitive here than it is to this. All right. And so if I have two coils and I do a full Fourier acquisition, then it turns out that a very good approximation to the least squares estimate is just this sum of squares recon, SOS. Okay, so when you see SOS or sum of squares, this is all that's going on behind the scenes. And you just take every image. I just take this image here, and I take its magnitude. This is already a magnitude image. I just square it, okay? And I take this one and I square it. I add the two together, and then I take the square root of the sum of squares. So that's all you need to do. But now let's talk about aliasing in MRI. And aliasing, remember, happens when we start skipping lines in K-space. So you saw that in your homework. And so that's essentially an undersampled acquisition. Okay. So basically, I'm skipping lines in K-space. In this case, I'm skipping lines in KY. And we looked at it from the Fourier point of view, which is basically I'm replicating my image, right? So that's aliasing. But we can also look at it from the minimum norm estimate point of view, which is essentially I'm finding that space that is can only is the minimum norm estimate is that estimate that is sort of can be represented by the sort of the Fourier components I've kept. Okay. And so remember that space, as you saw in the homework, is going to be orthogonal to the null space of my encoding matrix, right? And so what's in the null space? The null space is all those, is basically all those Fourier components I left out, okay? Including, I left out the Fourier component that would have like a frequency component like this, okay? Like a sine wave that would represent variation going, one full cycle across my image, okay? I don't have that Fourier component. And therefore, if you think about this, that's why I get the replication in this minimum norm estimate, because this object does not have that Fourier component where the top half and the bottom half can sort of be equal and opposite signs, right? So this solution is actually orthogonal to this sine wave. All right. So that's because it's orthogonal to the null space. So it's a minimum solution. So it's just that so whether we look at it from Fourier domain or from a linear algebra point of view, we sort of get the same picture. The bottom line is we end up with an image that we don't want, right? This is not a clinically usable image, especially if you want to sort of, do surgery like around this part of the brain. It's going to be very hard to sort of decide if you're seeing is an artifact or is actually sort of pathology that you want to deal with. Okay. So this is where we left off last time. And so the idea is that we could skip lines in K-space by just ignoring the outer lines in K-space, but that would give us a lower resolution image. Okay. So what we want to do is we're going to accept that there's going to be aliasing, and then we're going to take the leap of faith that we can undo the aliasing. So that's the sort of the magic trick that we're going to do. So the idea is we take advantage, we don't just have one coil, we have multiple coils, right? So the idea is this is an undetermined set of equations, but we actually have multiple coils, each one with a coil sensitivity here, C1, C2, C3. And now I've gone from underdetermined to overdetermined. So now I can have a solution that minimizes the error of this estimate. Okay. And there's going to be a unique solution for that least squares estimate. So let me see. So the key is we're going to use once again, we have multiple coils. So each coil here sees a different part of the brain. In this case, there's what, 8 coils, right? Now the problem is if we do this, the system of equations is really large. Okay, we get these huge matrices, right? And especially the more coils you have, you imagine this is just going to get bigger and bigger and bigger, right? So if I have 64 coils, I've got to repeat this 64 times. So you're going to end up with these really huge matrices. And it turns out it's just, if you try to do this in MATLAB, aside, like in the homework problem, I give you a very simple one where it's just 2 coils and the matrices aren't very big. But if I gave you anything that you would acquire on an MRI system, MATLAB would just say out of memory. It just wouldn't do it. Okay. So the trick is not that the theory is correct. It's just that the implementation of theory, people have had to be clever in terms of how they solve this problem. And so the two ones we're going to go over in this class are sense and GRAPPA, and we're just going to give you a sense of how they work. We're not going to go into too much of the details. Let's see. Is this the right? Okay. So just skip over that. I'm going to walk you through this and give you sort of a sense of how sense works. And then we'll show you that there is math behind it, but really just want you to understand how sense works from a very simple point of view and what can go wrong with sense and why we design the coils the way we design them. Okay. So here's the fundamental picture we want to look at. On the left-hand side here, I have 4 images, right? Each of them is aliased. Okay, you can sort of see that there's, let's see. Well, this one is obvious to see, but the other ones are aliased as well. So like here, you can sort of see this is coming into here. The reason why you don't see the aliasing as bad as if you had total sensitivity is because here where there's aliasing, the coil sensitivity here is dropping off. Okay, so where it would be if you had uniform coil sensitivity, you'd see the object much more aliased here, but the sensitivity is dropping off. And so there is aliasing there, it's just harder to see. All right. So let's look at each one of these. So let's look at a single voxel here. And then in coil 1, we'll call that value F1. We'll call this value F2, F3, and F4. Okay. That means for every voxel, I have 4 measurements of that voxel. Each of those measurements is aliased. Okay. So the question is, can I go from these 4 aliased measurements back to, in my original image, I had a true value IA and IB. Okay. Those are the 2 voxels in my original object that I'm assuming are aliased on top of each other. Okay. So for example, F1 is going to be what I care about, this value here, times its coil sensitivity, CA, for coil A. And then it's also going to be plus the second voxel times this coil sensitivity. Okay. And this is coil sensitivity of the first coil. All right. And so basically what I'm seeing is because we know the aliasing sort of makes things pop on top of each other, I'm just writing that aliasing explicitly. Yes, question?
How do you know what 2 voxels will be on top of each other?
Because remember, you know that because you know the Nyquist theorem. So you know like what the interval of replication is going to be. So once you set your, for example, your delta K, Y, then you know the image is going to replicate every FOV over 2. Or that's the FOV. So in this case, so for example, typically we say delta K equals 1 over FOV, right? So things replicate at FOV. Now let's say I double delta K, right? I skip every other line. So then 2 delta K equals 2 FOV equals 1 over FOV over 2. So that means I'm going to get replicas. If this is my original FOV, right? Now things are going to duplicate every FOV over 2. So basically, you've set up the problem so you know what the issue is going to be. Okay. So we can repeat this for every other coil. Okay. And you notice the IA and what we want to solve for is the same in every row here, right? I'm just changing the coil sensitivity pattern. Okay. And therefore, you can sort of see where we're going. We should be able to write this as a matrix equation, right? I should be able to solve for IA and IB, right? And the vector is just going to have these coil sensitivities in them. Okay. Yes, question.
Because addition, why does it get darker?
Sorry, why did I get what?
Adding the intensities,
Mm-hmm.
does it get darker?
Why does it get darker? Oh, because, for example, first of all, yeah, to keep things simple, we're talking about adding sensitivities, and in reality, we'll be adding complex numbers. But for this example, that doesn't matter. The reason why it's getting darker is, uh, so let's say in this case, the coil sensitivity is lower here, right? Than that alias part. The part that gets plopped here is it gets plopped there, but it's the sensitivity is so low there, its value gets downweighted. Yeah. So the darkness you're seeing is this basically, you sort of see this coil sensitivity here, right? It's very bright up here and it's much darker down here. So that's for one coil, and every coil is going to have areas that it's sensitive to. Okay. But so this is the basic idea behind sense, that I have this vector. So this is what I measure, right? I measure for every coil, I get an aliased voxel. And I say, I know that voxel value came from two image values, and I want to undo that. And I use these multiple measurements to undo that. Okay. So because I know, and that's essentially assuming I know these coil sensitivities. Okay. Then I can solve for this. All right. So that's the linear algebra problem. So that's all sense does. And it's pretty remarkable that it works, but it's basically it treats this big problem and says you can just go voxel by voxel. And basically, and this is sort of a common theme in like what's called numerical linear algebra, is if you can take a big problem and divide it up into lots of little problems, then you're set, right? And then you can do things like use GPUs, right? So then you're really set. Okay. All right. So that's why the best thing to happen to medical imaging is not only this innovation, but also gaming, right? Because without gaming, we wouldn't have GPUs. Okay. So, and then that also helped deep learning, right? So everything goes together. Okay, so this is just essentially just repeating what I just said. So just in a nicer format. So you don't have, if you want to look at this one, you can sort of see this one. It just doesn't have my messy writing, but it's the same answer. Okay. And then this, I'm just providing, I'm going to skip over this. This is just showing that if you actually went through all the math, you would actually get the same answer, but it would just take you like hours to go through the math. Okay. So I just gave you the sort of the answer, and it turns out that answer is correct. But if you want to, there's lots of papers and you can go through the math on that. Okay, so what I want to focus on today is more going through some examples, and these are essentially for the homework 6. You just run this code and look at it, and then all you have to do is put in your own profiles. So you're given two profiles to use, and you just come up with your own, and you comment on what you see, and that's pretty much just to get you to run the code and just sort of observe it. So we'll walk through these two examples so you have a sense of when you run the code what you're seeing. So I'm showing a 1D profile basically here, but the idea is if I look at the coil profile, since it's a 2D coil profile, I'm just showing you but it only varies in one direction. So that's the profile. So essentially, the coil 1 has this profile where it's sensitive here and it falls off here, and so the 1D view of it is just this, right? okay? And coil 2 sort of starts off low and goes up. So the 1D view of it is low and high, okay? And then I assume for my object, I assume some rectangular object. That's a true object. So if I look at that object through this coil, then obviously it's sensitive to this part of the object and less sensitive to this part. And same thing here. It's less sensitive to this part and more sensitive here. And then what I do is I add noise and I also do the undersampled recon. And so you can sort of see this is noisy and it's also got the aliasing, okay? And so this is what I measure, okay? So this is, each coil is going to give me an aliased version of the object with noise. And if I do the math, the sense recon, then I get my estimated object here, okay? Now there's this something called G factor, which we're going to get into and that you'll look at. And you sort of see these values of G factor around 2. This is sort of what's called a noise amplification term. It's become sort of a measure of how good this estimated image is. And so we're going to take another look at, so what we can conclude from this example is, this image is not too bad, right? I mean, it's noisy, which you'd expect. We've added noise, but overall it looks pretty good. And you notice these G factors, are fairly close to 1, and 1 it would be ideal. Okay, so that's good. So that's these two coils. If I have coils like that, they do a pretty good job of this sense recon. Now we're going to look at these two coils, which we looked at before when we did sort of the sum of squares. And so you sort of see these coils now sort of fall off much more slowly, right, in their sensitivity pattern. So you can sort of see there's a fall off here, but it's very gradual. And there's an increase here, which is very gradual. And if you look at the objects, they are fairly similar to each other, okay? There's just a slight shading. And if I do the recon and add noise, then they're aliased. And then when I try to create my image, I get something that looks pretty bad. All right, so basically, even though you would think that each image on its own actually looks pretty good, right, except for the aliasing, because they look so similar, they can't really undo the aliasing. And that, as you're seeing, it really amplifies the noise background. Okay, so this is what we're seeing is noise amplification. Go ahead.
Should we use then one coil in this case, if the shape or the profile of the coil is like this?
If you had one coil, then you wouldn't be able to undo the aliasing though, right? Yeah. So we're counting on the fact that you have two, because with one coil, if you undersample, then you're still stuck with that sort of wide matrix. So the only way we get around it is adding another coil to go back and get sort of enough data. Yeah.
Then I got confused with the second row
Yes.
of images that you're showing, because in the previous slide, you had.
Oh, the second row is just what would happen if you just multiplied the object by the coil. Yeah, so it's just like a thought experiment. Yeah, sorry, that's a good question. So this is sort of like, this is just showing you what the coil times the object looks like, but you don't have access to this, right? Remember, in MRI, if you knew that, then you wouldn't have to do the experiment, right? Okay, question. Yeah, so that's right. So the take-home message is if your coil sensitivities look fairly similar, the reconstruction is not going to look very good. Yeah, and we'll talk about that. And so that's also reflected here. This G factor, if you look at these values, it's like value of like 19. So the bottom line is in parallel imaging, we talk about what's called G factor. And so all you have to remember if you're seeing this is higher G factors are bad. Okay, higher G factors mean I've amplified the noise. Okay, and so you're really seeing that here. If you compare this image to this image, right? There's noise in the background, but and there's noise in the object, but it's fairly low compared to the image, my object itself. Here, the noise levels are basically on the order of my image of my object. And so this would not be a usable image. Okay. Okay, so let's talk a little bit about the linear algebra idea behind this. And this is sort of a concept that's sort of useful for all of sort of, I mean, if you're doing any estimation in science and engineering, then this is sort of the underlying concept behind what really determines your estimate. So for example, this is just some vector v1, right? And this is some vector v2, right? And I'm saying that my measured data can be represented as, V1 weighted by, let's make these vectors, plus a second vector weighted by I sub b. So let's call this vector f. Okay. So I've got some vector f, and I'm saying it's the sum of two things. And what I care about is I want to know these weighting coefficients. Okay. So let's consider two cases where, and we're just going to do a 1D example just to make it clear. So let's say V1 and V2 are orthogonal, right? That's the best case scenario, right? And let's say I have some vector f, right? Okay. And let's say, life is not perfect, so I always kind of have noise on that vector, right? So there's going to be a circle of uncertainty around the tip, right? That vector could be somewhere in that regime, right? But if you think about how it expresses vector on terms of these V1 and V2, it's going to sort of that uncertainty is just going to represent some uncertainty in, say, this is going to see some amplitude IA, IA and IB, right? So it's really not going to change my estimates too much of I and IB, right? In terms of how I add up those two vectors to get my noisy vector. But now let's say V1 and V2 are very similar. Okay. And now let's say, let me change the color on this. Whoops. Change the color to make this more obvious. Let's say my vector f is here, and it's got some uncertainty like this, right? Okay. So that means that one solution is sometimes my measured value might just line up with V1, and sometimes it might line up exactly with V2, and sometimes it might line up exactly with V1, and there's all possible combinations. In this case, then, I would say that, since V2 goes with IB would get all of I could represent this as, in this case, F just equals V2 times IB, right? And then IA would be 0, right? In this case, I could say F is just equal to V1 times IB, IA, and therefore IB is equal to 0. So there's a huge variance in my estimates, right? Because basically, since these two vectors are so close to each other, essentially, anytime my measured vector changes, how much I assign to either one of those changes a lot. So that's the basic idea behind why if you have what's called an ill-conditioned matrix or things aren't set up correctly, you become much more sensitive to perturbations. So perturbations in your observations then get amplified into perturbations in your estimates of what you care about. All right, so that's a very important principle to think about for basically all of science. Essentially, you need to make sure that the way you're setting up your experiment doesn't lead to this sort of noise amplification. Okay. Yes.
There can be cases where we get the exact solution, right?
In this case, yeah, because I've drawn everything in 2D, but in general, the model space and the measurement space are going to be different. Yeah.
So
In general, you're going to end up with something like this. F is going to be out here, and then the mod V1 and V2 are here. Yeah. But it's the same principle applies. Yeah. Question.
As to why we want to find V1 and V2, we do know.
Oh, we know V1 and V2.
Oh,
We're given V1 and V2, and I'm just saying that we pick V1 and V2, and those represent our coil sensitivities. So this is just saying if I pick V1 and V2 incorrectly, then the estimates of I and IB are going to be really bad. So I better pick them correctly. And that's just getting why people spend a lot of time designing coils. So the idea is if you just blindly design the coils and put it in the magnet, the images might look really bad. And so therefore people spend time thinking, what's the optimal way to design the coil such that the image estimates are good?
So they kind of reverse engineer it.
Yeah, well, we do a lot of simulations. So we actually calculate this thing called G factor, and we look at what is the G factor. So basically, and I'll show you some examples of that. So basically, for every coil, they actually generate well, let me show you. I think I have it here. Let's skip over it. Yeah, so this is actually a G factor map. So what you see here is, let's see. Yeah, so essentially what you're seeing here is, I think in this case, what they're doing is they're taking just, this is sort of a simulation, but they're taking two coils and they're just spreading them apart. Okay. So if the two coils are very close together, you notice that there are areas of very high G factor, okay, close to 5. Okay. And therefore you see the image is very noisy. Okay. And then as you spread those coils apart, it's almost like spreading those vectors apart because now each coil sees something different, right? And so now you sort of see the G factors are dropping down to 2 or 3, and the image is less noisy. Okay, so typically when people are designing coils, this is a very simplified example, but they'll come up with G factor maps and they'll say, okay, we want to keep the worst case G factor less than 2 or something. Or they might say, okay, overall G factor looks very good. There's a few hot spots where maybe it's a little high, but we'll accept that. So that's, there's always engineering trade-offs in the real world where, it's never going to be completely perfect, but you sort of do the best you can. Yeah. So anyways, let's see. So yeah, let's look at this example here, right? So this is, how do I get rid of that? Okay. So let's look at what the, go back to sort of thinking about the vectors that would correspond to this. So remember, we want to look at the coil sensitivity patterns, right? So for example, this one here for coil 1, let's say we pick a point here, -10, and then we go FOV2 over, half an FOV is there, right? So the two things in the coil sensitivity pattern we would enter would be, let's say 1 and maybe close to 0, right? For coil 1. And then for coil 2, it's going to be like 0 and 1, right? So this is the V1 and that's the V2. Those are very clearly orthogonal. And so I'm going to get a very good estimate, right? So when my coils are set up such that those two things are very different, I get a good estimate. Now, if I do the same thing here, like say I take those same points, right? Then I'm going to get something like 1.9, 0.91. Okay. In that case, these two vectors, V1 and V2, are fairly similar. And so that's going to lead to this huge noise amplification. And that's what you'll see actually, oops, where is it? Here. Basically, this is the G factor map for this one, and you can sort of see the numbers vary from like 1 to 1.2 when those two vectors are fairly close orthogonal. And here, they go from like, what is this, like 18 to 19. I mean, the scale is huge, right? It's a huge G factor. Okay, question.
Or the axis for the coil profiles?
These coil profiles?
Yeah, that's in the X and Y.
The axis would be essentially, this is the axis, right? I'm just looking at the profile going down.
And in the left curve,
Well, I mean, this profile is this profile, and this one is this one, right? Coil 1 and coil 2.
yeah, but I mean, when you say at -10, the coil profile is 1. -10, what do you mean by -10?
Oh, okay. Well, I think maybe look at the code, but I think I just didn't label this like so. Let's see. So this is yeah. So this is like, say this is 0, then this would be like -16 and 16, right? So just reference 0 is like sort of the middle line.
Distance?
Yeah, it's distance. Yeah.
It means the deeper you go, like the further away from the coil, I don't understand what the profile means.
The profile means if I'm basically every coil, like if I have a coil here, right? And the distance, this is 0 to like 32. If the coil is here, the profile would drop off like this, right?
Like the intensity of the.
Yeah, yeah. And then if the coil is here, the intensity would go up like this, right? Because it sees stuff closer to it. Yep, question.
Say the coils here, is it like if you were, sorry, so would it be pointing towards the top? Or would it be pointing towards the magnetic fields?
Oh, the coil can be in any position it wants. So for example, if I put coils around a head, right, I could just put I could put different coils around the head, or I could put a coil here, a coil here, a coil here.
The magnetic field is perpendicular to the skull.
Well, remember that, yeah, I mean, that's a great question. So it sort of gets into the trickiness of this. For example, if I put a coil here, right, there's not going to see, it's not, if it's exactly here and things are processing around here, the dPdt is going to not be, it's not going to see as much dPdt as here. So that goes into the coil sensitivity as well, like how sensitive it is to what's going on. So all that sort of stuff is wrapped up into how sensitive each coil is going to be to the magnetization, the processing magnetization. Yeah. So basically, luckily, there are people whose whole careers are doing this, right? They're RF engineers and they simulate so the simulation is you have a realistic model, E&M model of your of a head, for example, and then you simulate the coils and you look at all the RF fields, and it can be quite complicated, especially at 3 Tesla, you're sort of at the regime where the wavelength is still sort of slightly bigger than your object. But then as you go to higher, the wavelength of the RF becomes on the order of your object. So now you have to worry about weird reflections. And it's great if you like E&M, but it's good that there's people who know how to do it too. So it becomes a lot of E&M simulation. Yeah. Okay. Any other questions? All right. Okay. So anyways, all this, we're just going to skip over these slides. These are just telling you why, if you have any estimate, you can always look at the covariance of that estimate. And so this is something that's, in statistics and data science, you're always worrying about, what is the variance of your estimate? Okay. And so the way we define it in MR is essentially we have this thing called the G factor, which just tells you how much worse are you off than ideal. Okay. So G equals 1 would be ideal. Okay. R is acceleration factor. It's how much faster you went. So if I went twice as fast through k-space, R would be 2. And this is just sort of the derivation of the G factor. You're not responsible for the derivation, but just to show that there is a mathematical derivation, and that's how it's implemented in the code. Once again, you don't need to, you feel free to look through it, but that's just implementing the equation. This is really what you want to get at. Sort of the intuition I want you to leave with is just simply that how you set up your coil profiles translates into these vectors, and the relationship between those vectors will affect your G factor. So as you play around with these coil profiles, you'll look at your image and see how the image estimates looks, and you'll also look at these G factors, and you should sort of see that, oh, as my G factor is getting bigger, then my image estimate is actually getting worse. Okay. It's more like a guided tour through the code. Okay. Any questions on that? So that's all we're going to do is sense. So obviously, this is just a very high level overview of sense, but just to give you a sense of, what is done in practice. Okay. The other sort of very popular technique, and in some cases I think has taken over sense, is GRAPPA, which was invented later than sense, but as we'll talk about, has some nice properties to it, which make it fairly robust. And so this is why we'll spend some time talking about it. So the idea here is that if I have an object and I view it with some coil sensitivity pattern, then this is what representing what the coil sees. Okay. So I've multiplied my object by some sort of sensitivity pattern, right? Therefore, in the Fourier domain, what I've done is I've taken the Fourier transform of my object and I've convolved it with the Fourier inverse for the Fourier transform of my coil sensitivity pattern, and I get this. Okay. So each coil doesn't actually see the object. It sees a modified version of the object. Therefore, each coil's Fourier transform data is going to be the Fourier transform data I care about blurred out. Okay, so it's going to be a blurred version of the ideal Fourier transform. And so on the one hand, it's like, well, that's not what I want. On the other hand, that actually leads to a really cool trick that was invented for that. So the idea is if I have, let's say, different points in k-space, right? Right. Let's say, and we talked about if I have to go and collect all those points, it's going to take a lot of time to collect all those points. But if I know I blurred out the data, then I know, well, actually, these are not independent, right? Blurring, remember, it means I take any given point depends on the contributions of lots of other points. Okay, so blurring means that, for example, this point here depends on all these other points. okay, because of the blurring. That means, well, what if I just, maybe next time, I just don't bother collecting that point? If I have the points around it, then I can form an estimate of that point by just taking the right weighting of those points. Okay, so that's the idea behind GRAPPA, is essentially, I know my data is a blurred version of K-space, so there's a lot of data redundancy in K-space. Therefore, let's use neighboring points to calculate that point. And not only do I have from that coil, I have from all the coils. And so that's represented here, where essentially this is the missing point that I'm trying to calculate. I have neighboring points around it in K-space, and I also have the same view of that from different coils. So the K-space point for this coil, I can get information about it not only from its neighboring K-space points, but also from the neighboring space points views from all coils. And so that's the idea behind GRAPPA. And so it turns out that the idea behind coils that are good for GRAPPA or good for sense are also good for GRAPPA, right? Because if you think about these two coil profiles here, this falls off. So you know it's going to have some Fourier transform. Let's say it has some Fourier transform like that. Okay, let's say this has some Fourier transform like that. So it's going to do some amount of blurring of my image, right? Which makes sense because it's going to sort of window my image by this pattern here. Now think about this. This coil sensitivity pattern is much broader, right? So what is its Fourier transform going to look like? It's going to be much narrower, right? So this Fourier transform is going to be narrower, right? So it's going to do much less blurring, right? So then neighboring points aren't going to be as related to each other. Okay. So whether you do GRAPPA or sense, you sort of end up with the fact that the coils, essentially the coils need to see something different, which makes sense, right? Because if all the coils see exactly the same thing, then you can't really take advantage of the coil diversity to sort of make up for your undersampling. So the way GRAPPA works is essentially we start off with this undersampled data, right? And then we say, we're going to use that trick and just create a full Fourier estimate for us. Okay, we're going to go from this undersampled K-space data, and we're going to fill in all the missing points and get a full Fourier data set. So we're basically converting the problem into where we have all the data we need. And then from each of these guys, we can come up with an estimate of the image, and then we just do a sum of squares. Okay, so it's sort of a nice way of doing it. All right, so then it transfers, and there is a connection between sense and GRAPPA, but it's not easy to see. It's pretty complicated, but it's sort of obviously if they're both getting you reasonable images, there must be some connection. But it is sort of more advanced than we can talk about here. Okay, so these are some examples of images taken with GRAPPA, and so the acceleration factor just means I went twice as fast, 3 times as fast, or 4 times as fast. Okay. And you can sort of see here, if I start to go too fast, you sort of start seeing, for example, there's more noise in this image here, right? And you're starting to see some artifacts that aren't necessarily an image. So there is a trade-off. And so the trade-off is, sometimes it's okay to go faster, right? But then you give up some image quality. And so there's always this, when radiologists are setting up these protocols, they have to decide on, is it worth going twice as fast? Can I still get the diagnostic images I need? Or do I really need to go slower? Okay. So I would say that for a lot of clinical applications, people tend to be fairly conservative and go maybe 2 and 3 accelerations. But in research, where maybe we're willing to average over lots of subjects, we'll tend to go faster. We might go like 40 times as fast sometimes. We'll just go as fast as you can, okay? And hope that, the post-processing takes care of it, all right? So there's different trade-offs you make for research versus clinical. Okay. This is a nice sort of article in IEEE Signal Processing magazine that just sort of goes over these, but essentially what we've covered is either sense recon here, okay, or GRAPPA. And so those are sort of the 2 main approaches to parallel imaging. And everything is sort of a up to that point has been sort of a variation on that. Okay, but we've still sort of tried to solve the entire problem without even taking advantage of the fact that the images that we're looking at have a certain quality to them. There's some a priori information about the images, right? So if I do, for example, 16-bit images, it turns out there's a billion possible 128 by 120 images, and there's 17 billion possible 5 by 12 images. If I go to 32 bits, there's 70 trillion or 1 quintillion images, okay? So the space of all possible images is huge, right? But in reality, if we're looking at humans, we all sort of know what a human brain should look like, right? You can sort of imagine, if you've seen enough MRIs, you're like, okay, all human brains sort of look like this. And then when they're diseased, they sort of look like the normal one, but just have some weird things to it, right? There's a tumor or there's something. And so it turns out that the space of all biological structures is actually much, much smaller than the space of all biological images. So for example, these are images that have artifacts, and you can tell just because you know what images look like that those artifacts are not biological, right? They just look too regular to be biological. So we should be able to take advantage of that fact. Our algorithm should be able to say, these are not possible solutions, right? And we should only pick solutions that are within the space of biological structures. And so that's been sort of the first approach to that we're going to look at is compressed sensing, and then we'll go to deep learning, right? So fully sampled Fourier construction, okay, or even parallel imaging is designed to handle this entire space. Right? It's designed to say, okay, if I have to create images that are accurate over this entire space, then this is what I can do. Okay. And so compressed sensing and deep learning is saying, no. We only need you to get a good solution in this smaller part of the space. And if you can do that, then you can go much faster or have better looking images. So let's take a look at compressed sensing first. So here we're taking sort of our Shep-Logan phantom, doing the Fourier transform of it. And in this case, we're just randomly throwing out, I don't know, like over half the data. Okay. So in compressed sensing, one of the things is we throw out data, but we do it in a fairly random fashion. Okay. So incoherent sampling. And if I took these samples and just you're seeing here the minimum norm estimate, which we talked about, I get an image that's okay, but it's not great. And if I do what's called minimum total variation using a convex nonlinear construction, I get a very good image. Okay, it's almost like magic, right? I basically take the same input data, but as long as I do the right recon, I can get an image that's almost perfect. All right. So how's that done? Well, there's two things. One is data consistency. So this is what we've been trying to solve before, right? We're saying the measured data should equal so this is my measured data. So that's the data I measure. This is my image, right? Estimate. That's the estimate of my image. And this is my encoding matrix. So data consistency is essentially what we've been doing up to now in the course. It's just saying, I just want to make sure that what I've measured is consistent with how I did my encoding, right? What compressed sensing and deep learning do is they add something else. They say, well, and in addition, I want to find a solution that minimizes some other metrics, okay? In general, it's going to be my image estimate, M hat. It's going to go through some sort of transformation, and I'm going to minimize some norm or some estimate of the size of that transformed estimate. And one of the most popular ones is to choose phi to be a sparsifying transform, such as a wavelet transform. Okay, and this is based on a lot of sort of I would say in the 90s, there was a big wavelets was sort of the biggest fad in the 90s, and then it became sort of incorporated into like image compression methods, and so now it's sort of fairly standard, but it was brand new in the 90s, and people were just trying to figure out what to do with it. And one of the realizations that people came up with and why it's so useful for image compression is that if you take the wavelet transform of an object, right? For most objects that are natural objects, it's going to be a fairly sparse transform in the sense that only a few of the wavelet coefficients are going to be big, and a lot of them are going to be fairly small. And so you can do compression because you can say, well, I don't need to send all the small ones. I'm just going to send the big ones. And so you can save a lot of time. So this is the same idea. It's saying, of all the estimates I can come up with, right, give me the estimate that is sparse in the wavelet domain, because that's going to represent images that I think I care about. And everything else, you know, where there's lots of little values at locations that are not related to my image, I don't want to care. I don't care about those. Those shouldn't matter to me. So that's the idea behind the wavelet transform. So we're looking for a sparse transform. The solution that has a sparse transform is going to be part of our cost function. And so we're going to drive our solution to not only fit our data, but also to be sparse in this case, the wavelet domain. Okay. So this is some example here of showing, for example, in this case, I've done full sampling. So full sampling is Nyquist sampling. Question.
Do you go over the concept of a wavelet transform?
Yeah. So a wavelet transform is, so for example, like let's say this is the wavelet, this here is like the wavelet transform of this guy here. Okay, so this is my image, this would be its wavelet transform. And you can sort of see most of the values in the wavelet transform are close to 0. Okay, so if I want to like compress my image, I could just set all these to 0 and not send that data over. And so I only have to keep these coefficients. Okay.
What is it though? How does it get constructed?
Oh, how do you do the wavelet transform? It's just a it's just a mathematical decomposition. So the same way you type FFT, you could type wavelet transform of an image. Yeah. So a wavelet transform is essentially in Fourier transform, we have basis functions that are like sort of sines and cosines, right? Wavelet transform is just basis functions that look like that. They're essentially like they're essentially windowed windowed sines and cosine functions of varying width and things. So there's whole courses you can take on that, and some of you probably have, but that's the basic idea. Okay. And yeah, I mean, frankly, wavelet transforms and other transforms like that are also why, you have, are sort of why, there's so much video on the internet, right? Because you're not transmitting the whole video file, you're compressing it and sending a compressed version. And that's also why, for example, like sometimes, when you're watching TV, like especially with a big screen and something happens to your internet connection, you sort of start seeing like the initial image is sort of blurry, right? And it starts filling in the details, right? Because they send the low scale wavelet transform coefficients first, right? And then they keep adding the finer ones until they have sufficient things. Okay. And then, if you have moving images, then the idea is that, if you have something moving, then typically, like if the background stays the same and only something is moving, then you only have to encode what's moving, right? So there's just a lot of tricks that people have come up with over the years. Okay. So this is just showing you, for example, how well you could do if you did the full Nyquist sampling, which we've been doing. If you got rid of the outer parts of K-space, right, you could go faster, but then you have a low resolution image. If you just a sort of a standard recon, it doesn't look so good. Also throwing out some of the data. But if you do compressed sensing, you get something that's quite good, okay? And you've gone much faster. And I believe these are just some other examples for, let's see. 1A and D are the full sampled. So over here, you're seeing fully sampled. And then here, you're just going faster, okay? And here's another case where compressed sensing really works well, because in angiography, where you're just looking at the blood vessels, you have really high value. So this is naturally sparse image, right? Because basically, most of the image, only the vessels are bright. The background is sort of like noisy, and you don't really care about it so much. And so you can actually also compress this very well. And so this is an image where it works very well with compressed sensing, right? Okay, so that's all we're going to talk about compressed sensing. I think there might be one project on it. I don't remember, 1 or 2 projects on it. Okay. So now we're going to just give you sort of an overview of deep learning, because that is sort of where the current state of the art is, and just to give you a sense of why deep learning makes sense and why it could work. So this was really the first paper. So it's not that old. So this is a paper published in Nature in 2018. So this was really the first. So 6 years ago is really the first demonstration, or around then is when deep learning first became sort of used. And so this was sort of what's called end-to-end deep learning. So they just started off with the K-space data, and they had the deep learning network learn everything up to the image. Okay, so that was the first attempt, and it's something called AutoMap. It's something that you can just go to their GitHub and download the code, and you can do it yourself. So it's definitely possible to do. So essentially, they have a bunch of fully connected layers right here. Okay, and then they go to a bunch of convolutional layers. Okay, so it's not even a very deep network. And so it was sort of amazing. I think when this first came out, people were quite amazed that it could do such a good job. And this is what it can do. So for example, here, what we're showing you here on the left are different K-space trajectories, okay? Here is a radial, or they calling a radon projection, where you're going through K-space in radial spokes, okay? Here you're doing your spiral, okay? So you did a square spiral on your homework. This is our Archimedean spiral. Here we've just undersampled, so sort of like compressed sensing. And here we've purposely misaligned the Fourier space. So basically, what it's showing you is every other line is sort of misaligned. Like you want to acquire like lines in K-space like this, but you just like went back and forth and you just made a mistake. Okay. So let's see what happens with that. So AutoMap is their method, okay? And conventional is what you would do if you used the best state of the art at the time. And you can sort of see for the radon trajectory, they do much better, much more sharp images. For the spiral, much better as well. And here, the main difference here is also this recon would probably took about 8 hours to do. Okay, this recon was probably less than a second. Okay, now they spent a lot of time training the network. But the nice thing about deep learning is once you train the network, then the recon's very fast. It's just feed forward typically, right? Whereas with things like compressed sensing, you're iterating and spending hours sometimes looking for the solution. Okay, so that's another advantage of deep learning. Here, if we look at sort of this image here, compressed sensing does pretty good, but remember it takes a long time to do. And here, the image quality with deep learning is quite good. And then here, where there's all that artifact, if I just did a straight inverse transform, I get all this aliasing, and the deep learning knows to just fix that. Okay, it just says this cannot possibly be a solution. So I'm going to find a solution that makes more sense, right? And so one of the interesting things about the deep learning network is that after you get through these fully connected layers and one convolutional layer, if you look at sort of what that convolutional layer is using to sort of make up the image, these are the features of that convolutional stage, okay? And the interesting thing is they just sort of trained this on using things like ImageNet and things like that. And so what you notice is the network itself sort of found Fourier components. Okay, basically by training all this data, saying this is the input data, this is the K-space, and this is what I want, it naturally figured out how to come up with Fourier transform on its own. Okay, so it's quite remarkable. And these are just more examples showing. And here you can sort of see the acceleration is quite a lot. It's 4x4. I mean, so they went 16 times as fast, right? They accelerated 4 times in kx and 4 times in ky. They really pushed it. And so you can sort of see here that if you look at the error for AutoMap, it's much less than the error for Sense. Okay, Sense can still do a pretty good job, but AutoMap does very well. And it also does very well in low SNR regimes. So for example, here is where they're taking SNR of 13.2 and then lower SNR here with conventional image. And you can sort of see here that the AutoMap, even though, let's see, what is it doing here? Oh yeah, no, I think, I don't remember the details, but the overall SNR of AutoMap is much better because essentially it learns that because it's been trained on sort of good images, it knows that anything that looks noisy is also not part of the solution it wants. And so it automatically figures out how to get rid of the noise as well. Okay. I think here on the bottom, yeah, you can sort of see here, it's doing a good job. All this speckly stuff you see here, all this, sort of this salt and pepper pattern, you don't really see this here in the AutoMap image, right? Because it's basically it knows to take out that salt and pepper pattern. Yes, question.
For getting rid of the noise and getting the edges sharp again, it would just have to assume some edges that are not there, given the data we have, right?
Essentially what it does, we'll come back to that in a minute, because it is, as those of you who have done deep learning know, then yeah, I mean, the question is always, to what extent did it just make things up? Right. So that's where we're at now, is, in terms of the adoption of deep learning, what I would say, and we'll get into this a little more, is right now, I think deep learning is here to stay, but people are being fairly conservative in adopting it, especially for clinical application, because you don't want to like go to surgery because the deep learning hallucinated a tumor, right? And you open up like, well, there's nothing here. Okay. So I don't think we're at that stage, but that is the concern. Okay. So this is actually just published, I guess, this year, Deep Learning for Accelerated and Robust MRI. So those of you doing that, this is, goes through sort of the fact that there's lots and lots of methods now for deep learning. So a lot of work has been done in the last 6 years, actually, in this area. So the case space to image network is what we just covered, is the AutoMap. But as you can sort of see, and we'll get into, there are other approaches that might use like UNet or ResNet, which some of you I know are familiar with. And so let me just give you a sense of the approaches that people are using. And the idea is that people are just trying lots of different things. The same thing with deep learning, like when you ask someone about why does this architecture look the way it does, it's sort of like, we just tried it and it worked. Okay. So there's still a lot of that going on. So I think there's still room for people to think about it. But here, for example, we start off in case space and we do an inverse transform and we get a reasonable looking image. And then we count on the deep learning network to make it better. Okay, so this is what's called image domain learning. Where, for example, maybe you start off with an aliased image and you make the deep learning network get rid of the aliasing. Okay, so that's image to image. Okay. And then what we looked at with the AutoMap is I go directly from case space to my image, and that's called domain transfer learning. So directly from case space to image space. And then you have hybrid approaches where, for example, you might do let the Fourier transform do some of the lifting, get a reasonable looking image. And then you might also go directly from this space to here, okay? And then just have a combination of the deep neural network and the Fourier transform, once again, create your image, okay? So there's ways of sort of using a deep learning network for part of it and using the Fourier transform for part of it. And there's also sensor domain learning where you actually make the deep learning network. So let's say there's a problem with this case space. You make the deep learning network clean up your case space first. Okay. So for example, this might be something like GRAPPA, right? Where, for example, you give it where it's missing parts in case space and the deep learning network could fill in those parts. And then you could do the transform. Okay. So there's lots of different approaches. And the real excitement about deep learning is from this graph. This is imaging time, how long it takes. This is recon time, how long it takes to reconstruct the image, right? So conventional imaging can take a while, as we saw, but the reconstruction is typically very fast because it's Fourier transforms, okay? Compressed sensing allows you to reduce the imaging time, but it's no good if it takes hours to reconstruct, right? Because then you've done the exam, but now if you have to wait an hour to do the diagnosis, maybe that's too long, okay? So machine learning allows you to go faster, and the recon time is super fast because it's just GPU based, just a bunch of forward calculations. Okay, so that's why there's a lot of interest in deep learning. So we're just going to give one view of deep learning to sort of tie it back to what we've talked about so far, which we've talked about this forward operator, or we've called this the encoding matrix, for example. Okay, so either we use E, but in this case it's A. And we just said, we take our image, okay, and it goes through some transform and gives us our case space data, okay? And in this case, once again, the matrix is wide, right? So we know there's multiple possible solutions. And so there's many, many, many possible solutions, right? Right, because anything that has a component in the null space, I can add it on, and it'll be a solution. And so the idea is, how do I go from all these multiple solutions to a solution that I think is the best solution that best represents what I care about. So for example, the question is, we know that if we undersample the data, we're going to get aliasing, right? So can I go from, for example, this is one possible solution, and can I say, I want to go for, I know there's something in the null space that's being added to that. Can I go to something like this, where I'm in the place where I haven't added those artifacts on? Okay. And so the key is I need to find a solution that is part of what's called the image manifold. Okay, and that's the job of the training, is to figure out what this manifold is. And so the manifold is essentially this low dimensional subspace, which can be very curvy overall, but in any region it looks fairly linear. Okay, so that's all a manifold is. All right. And so what these deep learning networks are doing is they're saying, well, I basically want to just sort of find this weird shape thing, which neural networks are really good at, right? And I want to project, my solution needs to be part of that low dimensional manifold. And I'm looking for whatever is on that low dimensional manifold that also fits my data, and that's going to be my solution. All right. So that's essentially what it's doing. And so if you want to learn more about that, there are some textbooks out there now on this, actually, that I think the library has. So you can download these through the library. And essentially, the other thing deep learning network does is that sort of, I think these groups have figured out, is the neural networks, because they have these, I think everyone probably has some sense of deep learning networks. There's these nonlinearities in them now, right? Right. These like rectified linear units, right? So if everything was linear, then it'd be limited. But because it has these nonlinearities in the deep learning networks, it's able to sort of say, okay, if I get a knee image, I'm going to put you in this solution space, and it optimizes you there. If the input data looks like it's coming from a brain, I'm going to put you over in this solution space. So it's actually able to sort of almost assign you to the right space, because it has these sort of, every nonlinear unit is almost like a decision point. Okay, so that's showing you here where it's dividing the solution space into like heads versus, I guess that's a cross section through a leg. Yeah. Okay. So the idea is because heads look different from legs, look different from hearts, and so what optimizes the manifold for heads is going to look different than what optimizes it for bones or for kidneys or lungs or liver. Okay. So this is sort of this is the last few slides I'm going to go through today. So there was a competition. There might be a more recent one, but this was the 2020 Fast MRI Challenge, where anyone could enter this, and a bunch of companies and even some labs entered that. And essentially, they were given data to train on, and then they were allowed to test data, and then there was some unknown challenge data that basically, so they could use the training data and the test data to train their networks, and then the actual test was done on the challenge data, which they didn't see. Okay, and it's not been published at all. So only the people at NYU who ran this experiment. So this is, I think, between NYU and Facebook sort of had this sort of challenge set up. And then also they had a transfer track where they also said the training data was from a Siemens machine, but then they also gave it data from GE and Philips and said, okay, if you trained your deep learning network on Siemens, how well is it going to transfer to GE and Philips, which you've never seen that data before. Okay. So that's sort of what they did. And overall, they found that they did pretty good. But in certain cases, for example, they did find that the deep learning networks would hallucinate. Okay, so for example, this is the ground truth. So essentially, this is the fully sampled case space data. So the ground truth is like you keep all the data. 4x means you go 4 times as fast. Okay, so you throw out to go 4 times as fast, you throw out basically 75% of the data, right? A lot of the data. Or you go 8 times as fast, so you throw out a lot of the data. And so in this case, for example, you can sort of see if you zoom in on it, the deep learning network hallucinated this. Okay, so it added that to the image. Okay, so that's obviously not something you would want. In this case, the deep learning network hallucinated that. Okay, and here it looks like, what did it do? It added sort of this bright thing that doesn't really exist in the original image. Or actually, what did it do? But yeah, it actually closed. So if you look at this versus that, it actually changed the structure quite a bit there. Okay. So this is one of the things where, and these are like state-of-the-art deep learning networks, and you said still once in a while there's still some issues with hallucination. They also compared methods from different groups. And so, for example, what they found was these were like the 4x and the 8x submissions in terms of 4x is going 4 times as fast versus 8 times as fast. And you can sort of see here, I think the group that sort of did well overall is the Ayers Medical Group, which was founded by a bunch of PhD students in South Korea, and now they have businesses selling this software. And you can sort of see here, if we look in, let's see, how can I zoom in there? So if you look here, and we'll talk about what causes this here. This is what's called a susceptibility artifact. Their recon does a pretty good job, not perfect, but sort of see how there's sort of like almost 2 lobes to that. So this is pretty good. Sorry. Yeah, no, it does a very good job. So this is the ground truth. So the Ayers recon does a very good job of sort of showing that there's like 2 sort of lobes of that, whereas these other 2 recons just sort of merge it into one. Okay. So there are subtle differences between the recons, and so I think people are still working on that. Okay, so I think we'll end there. Yeah, we'll just stop here and we'll start relaxation on Wednesday. And so what I'll do is I'll end it a little early, and so I can take questions on either the homework or projects if you have them. All right. Okay. Any questions that people want to add for the whole class? Okay, and I'll stop the recording. Oh wait, there's a chat. Let's see. Okay, the question is, where does the random sampling relate to the sparse transform? The random sampling is just to sort of create an incoherent pattern so that the aliasing sort of is incoherent. And then therefore, if the aliasing is incoherent, then in the transform, those will tend to go into the smaller components that then can be sort of thresholded out. Okay, it's a good question. All right, so let me just stop this recording.